Hello, it's Keith here, and this is lesson 58 of the platform-specific series of my 68000 assembly programming tutorials. We're looking at setting up interrupts on the Atari ST today. We've got this example here. This is my Mintile example, the graphics routine, and we've added sound to it via my ChibiTracks music player. We're not going to look at the graphics today. What we're going to look at is how we can get the Atari ST to fire an interrupt at VBlank, and then in this case we're going to use that interrupt to actually time our music so our music plays at the right speed. Now, usually in these tutorials, on my tutorials, I try and avoid using the operating system, but in this case I don't know that it was possible. It certainly wasn't plausible from my level of experience to get VBlank working without the operating system. So what we're going to do is we're going to hook into the operating system and we're going to ask it kindly to run our routine whenever VBlank occurs, which is actually pretty easy. Now, on the Atari ST, there's actually a table of addresses to execute during every VBlank. So all we need to do is find the address of that table and find an empty slot in it, if there is one, and actually add our interrupt handler to that list of entries, and it will be run at VBlank. Now, the address of the table is at memory address 456. So that's the address, and there is also a count of the number of entries there at 454. Now, generally speaking, that will be 8, but we probably shouldn't assume it is 8. Now, what we want to do is we want to find an entry in there which is 0 if there is one. So what we will do is we will basically load the address of the first entry from that 456 address, the count in 454. We're going to test an address, and if we find a 0 there, a 32-bit value 0 there, we're going to branch to this routine here, found one, and all that does is it loads the address of our interrupt handler into A0, the address that we just checked. So we're just loading our interrupt handler into that position. Now, if we didn't find a valid slot, we're moving to the next slot, we're decreasing our count by 1, and in the case that we don't find a valid interrupt handler, we're just going to give up and return. Now, I suppose actually we could be a bit cleverer, and maybe we could actually sort of hijack one of the existing interrupt handlers. Maybe we could take that last entry and we could execute our interrupt handler and then jump to that other interrupt handler instead. I suppose that would be one solution. But for today's simple example, there's never a case where there's so many interrupt handlers installed that it's a problem. So we don't need to worry about that. So in our case, we will always find a position for our interrupt handler and we install it like that. So that's pretty straightforward and it works just fine. So that's how we install our interrupt handler. And to be honest, there isn't actually anything our interrupt handler needs to do. It looks like the operating system actually backs up the registers for us. So I've disabled my code that I usually use to back up and restore all the registers. We are actually not returning from the VBlank interrupt. We're actually passing control back to the operating system. So we're returning with an RTS, not an RTE. If we were actually truly handling the interrupt, we would be using an RTE, return from exception, but we're actually letting the operating system do the work. So we're returning from subroutine as normal. So that's all our interrupt handler does, very straightforward. Everything else is done by the operating system. Now, we're just going to briefly discuss ChibiTracks. That's my music player. ChibiTracker. ChibiTracker Pro is the Windows software that makes the music, and ChibiSound Pro is the platform-specific sound driver. Now, I've covered all of those in separate tutorials. It's just the interrupts we're looking at today, but I'm just going to briefly cover how ChibiTracks has been set up here. So when we want to update our music, we run ChibiTracks Play. That updates the music and the underlying sound hardware. The ChibiTracker needs a little bit of memory, so we're defining in the user RAM at the bottom of our program here, we are defining some memory for ChibiSound RAM here. It needs about 256 bytes on the 68000 systems, 128 on the Z186502, but a little bit more on these systems. So we're defining the offset to the song and the bass and the channels and the speed. These are all parameters that are actually initialized automatically by the music player, but we just define those variables as part of the ChibiSound RAM. The rest of the RAM is used by the platform-specific player. Now, ChibiTracks is actually here. You can see the code that makes it up. ChibiSound Pro is the platform-specific sound driver, so there is a module there for the Atari ST that handles the underlying Atari ST hardware, and it basically abstracts that hardware and passes a common routine that ChibiTracks can work with. So ChibiTracks is multi-platform. It asks ChibiSound Pro to do the settings it wants, the pitch and the volume and things, and the platform-specific driver does that job. The binary file, in this case the Chibi Akima's theme here, is we've called it song 1. This is a multi-platform binary, so you can play the same music file on the Z80 systems, 6502 systems and 68000 systems, and in theory more if you ported the player, without any changes to the binary file at all. So this file was originally exported for the Amstrad CPC. We're playing it on the 68000. You can play it on the Amiga, the Genesis, the PC Engine, anything, any platform. That's what it's there for. It's designed to be a fully multi-platform system. So that's what we've done there. So yep, that's what it's intended for. Now so that's how we get our binary file in and how we update it. The only things we need to do to actually start it is simply run Chibi Sound Pro init. That initializes the platform specific sound driver. We then load the address of the song we want to play into song base, which is one of those variables we saw before in the tracker software. That's the only one that doesn't update itself. And then we run start song, which loads up all of the parameters from the binary file and gets things ready to start playing. Now, if we want to be clever, we can actually change the playback speed of the song. We don't need to on this system, but if we wanted the song to play much faster, we could put a lower number in here. The default play speed is actually 5. On a 60 Hz system, we need to change it to 6. But if we wanted to make the song play super fast, maybe the player's running out of time, like in Super Mario, and we want to really pile the pressure on them, let's make the music play faster and really wind them up. So you can hear there the music is playing very fast indeed. Yes, I don't think they're going to like that noise. That's going to get them speeded up. Anyway, not something you need, but it's an option that the player can provide. The default speed is encoded into the binary file by the tracker. So there we go. So that's what we got today. As I say, always you can go to my website, download the source code and the build scripts, and you're welcome to use them in anything you can. You can also get the tracker. The tracker is also written in .NET. It's free and open source. So if it's any use to you, please go ahead and use it. Anyway, hope you've enjoyed what you've seen today. Thanks for watching and goodbye.